So if the very easiest case, if I just look at the reciprocal of a function, so I've got the function 1 over v, and we're going to be taking the derivative where the denominator is in 0, because that would be outside the domain. And we'll want to show that this is equal to negative 1 over v squared dx, or dv dx. So let's go through our standard procedures. So the first thing we need to do is compute the change in 1 over v, which is 1 over v of x plus delta x minus 1 over v of x, which combining as one fraction is v of x minus v of x plus delta x over v of x times v of x plus delta x. And notice that the numerator is almost the change in v over is almost the change of v. It's backwards, right? The change of v is always you evaluate at x plus delta x and subtract v of x. So this is just, got a negative sign in front of it. So this whole term right here is negative delta v, right? Which would be negative v of x plus delta x minus v of x. So the numerator is negative delta v, and so we will use that in computing our derivative. So the derivative of 1 over v with respect to x, always going back to first definitions, this is the standard part of the change of 1 over v with respect to the change in x, which is the standard part of negative delta v all over v of x plus delta x. All that, of course, divided by delta x. And simplifying that fraction, and I'm also going to pull this negative out. So this is equal to negative standard part of the change in v over the change in x times v of x plus delta x. And this fraction I can break up as a product. I'm going to look at it as delta v over delta x times 1 over this whole thing. So breaking that up and using my standard part to distribute across multiplication, this is simply negative standard part of change in v over change in x times the standard part of 1 over v of x times v of x plus delta x. Sorry for squishing that in there. Now, the standard part of v over x, that's just the derivative of v with respect to x. And now the standard part of this here, v is a real valued function, so v of x is just a real number. And if I slide my standard part into the function here, x is real, delta x is infinitesimal, so I end up with that this is equal to negative derivative of v with respect to x times 1 over v of x times v of x, which is much more natural to write this way, negative 1 over v squared dv dx. Or in other words, we get that the differential of 1 over v is negative 1 over v squared dv. So we'll use this now to establish our quotient rule. So let's get down, get some room. So the quotient rule, now we're looking at not just 1 over v, but now we could have some arbitrary function, u, in the numerator. But we'll use the process we had before, using the idea that we already know what the derivative of 1 over v is, and we can use our product rule, because the derivative of u over v with respect to x really is the derivative of u times 1 over v dx. So this is equal to our derivative of u with respect to x times 1 over v plus u times the derivative of 1 over v with respect to x. Right? It's just our product rule. It says that the derivative of the first times the second plus the first times the derivative of the second. That was our summation rule, or sorry, product rule we derived in the previous video. So now du dx, that is what it is. This right here we just computed in the last step, and so this is, let me write this way, 1 over v du dx minus u over v squared dv dx. And if I want to put this under one simple fraction, my common denominator is v squared. So I get that this is equal to v du dx minus u dv dx, all divided by v squared. And this is kind of cumbersome to write, which, and you'll see in subsequent exercises that I will more often use the differential form, which is much more concise, or I guess easier to deal with, saying that d differential of u over v is simply equal to v du minus u dv over v squared. So now, just like before, we got u to the n, but now we're going to let n be a negative integer. So we know that n is negative. But that means we can think of n as being equal to negative m, where m is positive. In fact, we know exactly what m is. It's the absolute value of m. So when we look at the derivative of u to the n with respect to x, we rewrite it as the derivative of u to the minus m with respect to x, which algebraically is equivalent to 1 over u to the m with respect to x. And we've got it in a form that's a quotient rule. So using our quotient rule, this is equal to the derivative of 1 with respect to x, u to the m, minus 1 times the derivative of u to the m with respect to x, all divided by u to the m squared, so u to the 2m. Now, this first term is a constant, right? 1 is constant, so d1 dx is 0. The derivative of any constant is 0. And this derivative right here, we know from our basic power rule, because m is positive, the differential of u to the m dx is equal to m u to the m minus 1 du dx. So using those two facts, this whole expression simplifies to simply minus m u to the m minus 1 all over u to the 2m du dx. And now I'm going to replace the m's back with the n. So remember, n is equal to minus m up here, right? We set n equal to minus n. So this I can rewrite as n times u to the minus n minus 1 all over u to the minus 2n du dx. And doing a little bit of algebra to clean this up, this is equal to n times u to the 2n minus n minus 1 du dx, which is equal to our familiar n u to the n minus 1 du dx. So the same format works whether our exponent is positive or negative now. So we've extended the power rule to negative numbers inclusive. And that proves all the basic formulas that we're going to need for dealing with rational expressions. In the next video, we'll run through a bunch of examples employing these rules.